Namaste. Welcome to this channel, Dr.ARM's Chemistry. We were discussing theories of acids and bases. We have seen up till now number of such theories such as the Arrhenius theory, Bronsted-Lowry concept, then Levy's concept or solvent system, etc. And in that case, we have to also consider the strength of the acids and bases. So here we are discussing this acid-base strength, and in this point we have also considered several other points which are used to measure the strength of the acids and bases. Today we are discussing the strength of the acid and base in terms of especially for this oxy acids. We must know that this oxy acid has general formula like this: EOM. E is here any element such as electronegative element. For example, we can consider here we can say fluorine, chlorine, bromine, nitrogen, phosphorus, etc. And the oxygens here are any number. It may be 0 or any other, but this oxygen is non-hydrogenated. It is not attached to any hydrogen. And this OH is the oxygen which is hydrogenated, which is bonded to the hydrogen. And N is the number of such hydrogenated oxygens. N is the number of such non-hydrogenated oxygens. So we are considering here these some examples. So this is HClO4, HClO3, HClO2 and HClO. Now, if we see the strength of such acids, we find that this is the strongest acid, and the order of the strength of the acid or strength of the acid is in this order. So this is the strongest acid. This is the relatively weaker one. So strength decreases in this direction. So we have taken here this element E as the chlorine. We can have also such nitrogen, phosphorus or any other such elements. Now if we see the structure of these compounds, then we find that this chlorine is attached to this oxygen, say having one hydrogen is bonded to this oxygen, and this chlorine is further bonded to these oxygens. So we can have such structure. So here this negative charge is distributed on such non-hydrogenated, or electron density is concentrated on this non-hydrogenated oxygens. So here you find that there is only this, the number of such oxygens, non-hydrogenated oxygens, here N is equal to 3. In this case, similarly you can have HOCl. Like this. Similarly, you can have here a H. Like this. So here we can have such different number of oxygens which are non-hydrogenated. Pauli considered this number of non-hydrogenated. Pauli considered this non-hydrogenated number of oxygens to calculate or approximately understand these pKa values. So according to this Pauli's equation, the approximate pKa value is given by 9 minus 7 into n. 9 minus 7 into n. As a result of this, we can have this pKa values for these acids. So you can find here this pKa values. You can have different number. So here 9 minus 7, here n is 3. So 9 minus 7 into 3. So this gives us minus 12. So this gives us minus 12. So in this way we can find in this case also this 9 minus 7 into this 2. Here 9 minus 7 into 1 and 9 minus 7 into 0. So in this way we can calculate the pKa values as approximate values which are indicating the approximate strength of the acids. Similarly, another scientist, Bale, who has also given the similar equation, that is Bale's formula, we can say, which shows that this pKa value is approximately equal to 8 minus 5n. 8 minus 5n. In this way, there are two equations we can see in order to understand the approximate pKa values for different oxyacids. So on that basis we will see these examples. For example, HClO4, HClO3, HClO2 and HClO. Here you will find that this n is equal to n, the number of non-hydrogenated oxygens. Here it is 3, 2, 1 and 0. Then we can have these Pauli's equation, that is 9 minus 7n, and Bale's equation. It gives 8 minus 5n. So on this basis we can calculate here, that is minus 12. Here we can have how much? 2 into 7, 14, and this 9 means minus how much? 5, and when it is 1 it is 2, and when it is 0 it is how much? 9. Here it is 7 into 0 means 9. So in this way we can have the variety of values. So similarly, according to this equation, we can have the values when it is 3, 5 into 3, 15. So it is minus 7. So in this way we can have here when it is n is equal to 2, it is minus 2, when n is equal to 1, it is 3, and when it is 0, it is 8. So in this way, these are the actual, means approximate calculated values according to Pauli's equation and Bell's equation. But if we see the practical values, or we say experimental values of pKa, then we find that the values are not matching every time with either of these equations. So actual experimental value is -10, experimental value. Similarly, in case of this -1, and in this case it is 2 and 7 point. So if you see which value is matching, no value of these two is matching with this -10. It is below this Pauli's value and above this, or we can say it is not correctly matching. Similarly, these two values are also not matching. This only matches here, and these are not also matching with this experimental value. It means these values are approximate, and experimental values are also uncertain to predict the pKa values, means strength of the acid in this way. So in another case, we will see, if you take this other example of is P phosphorus. In case of phosphorus, we can have the compounds such as H3PO4, then H3PO3, then another is H2PO4 minus. Taking this H3PO4, H2PO4, H2PO4 minus, and HPO4 2 minus. HPO4 2 minus. So here we can have, here we are also considering the non-hydrogenated oxygens and hydrogenated oxygens in order to, means according to these same equations. So we can have, see, this n is equal to, so n is equal to, here you will find that this non-hydrogenated oxygen is 1. In this case, non-hydrogenated oxygen is not available here. Okay. So we can show this H3. So we can have these non-hydrogenated oxygen. pKa values are found to be here 2. pKa values, these are approximately according to 9 minus 7 into n. So these are the 2, 7 and 10. So again, in case of, or according to another equation, that is pKa approximately equal to 8 minus 5 n. The values are 3, 8 and 13. 3, 8 and 13. And here the experimental values, pKa experimental values, you will find that these are 2.15, then 7.20, then in case of here it is 12.37. So here you will find that these experimental values are matching in some according to this formula here, but here it is also matching with this first Pauli's equation, and this is also matching, not matching exactly, but it is lying closer to this equation given by Bales. So here the explanation shows that the each means, here you will find that each non-hydrogenated oxygen provides the electron density, rich electron density or high electron negative nature, and this oxygen will, non-hydrogenated oxygen of this will attract electron density from this phosphorus. There it is, phosphorus. If you see the structure of this phosphorus, we can see here OH, OH. So here we can have this non-hydrogenated oxygen. It draws electron density towards this or away from phosphorus. As a result of this phosphorus withdraws or draws electron density from these OH minus. So again, if you see here, we can split this structure again here in this way. So we can show this as hydrogen. So you will see that when this oxygen, non-hydrogenated oxygen, withdraws, because it is more electronegative than this, so it will withdraw the electron cloud of phosphorus. As a result, phosphorus becomes electron deficient. It withdraws again electron cloud or bonding electrons of this OH bond towards itself. As a result, this bond becomes weaker. So this bond becomes weaker. As a result, the hydrogen can be easily lost. So minus H plus. And because of this, we can see the greater the ability of these hydrogens to be lost by this acid, it will be stronger acid. Means greater the number of such non-hydrogenated oxygens, stronger will be the acid. So as a result, this is the stronger acid, this is relatively weaker acid. So in this way, the strength of the acid decreases as the non-hydrogenated oxygens increase in number. So we can have such structures. Again we will see that here you will see that the negative charge on this oxygen, is distributed only over this oxygen. And if you see the after loss of 1 more H plus, we can get this structure. So there is such oxygen. So you will find that this negative charge is distributed on both of these oxygens. So here you will find that there is distribution So this negative charge is moving here and it will be distributed like this. So each bond gets 1/2 negative charge. So in this way the negative charge distribution on oxygen is observed, and here you will find that greater the number of such oxygens which are showing charge distribution, then greater is the strength of the acid. Here we can find we can have such number of examples where we can calculate the approximate pKa values on the basis of this Pauli's equation and Bell's equation. So you can try many such examples at your own level and using these equations. So we will stop our discussion here. Please subscribe to this channel, press bell icon and like button. So thank you very much for watching this channel.